and we'll continue. Okay. So the objectives of this lecture is going to be the following. We're going to talk about the advantages and disadvantages of static routing, and that's something we have done last week. And we know already static routing, the issue with that is it doesn't do well when the network is large. Imagine doing the setup for each network you have. So it does not scale well with large networks, and it's manual. So if you add any other device to the network, you have to do the setup manually for all the routers there. Then we're going to talk about the role of dynamic routing protocols and place these protocols in the context of modern network device. And these protocols will provide the solution for the issue that we faced in static routing. Identify several ways to classify routing protocols. There are things based on like the area or the region, and describe how metrics. We're going to talk about the concept of metrics and how they are used by routing protocols to identify the, let's say, the metric types and the best path based on the metrics. And there is a metric called administrative distance of a route, and to describe the importance of the routing process. So the higher will be the better. And then we're going to talk about in Packet Tracer, we're going to show things that the different elements of routing table. All right, so what is routing? You probably know routing is the process how the routers move the messages or the packets between, let's say, the elements of the network. So it is a process that a router uses to forward packets towards the destination network. A router makes decisions based upon the destination IP address. Remember when we used the headers thing? So we have the original packet, and there is TCP header, and there is the IP header. So this one is TCP. This is original segment. This one that carries the data. And this one is the IP. And the IP header contains information about the source and destination IP addresses. So the router will make the decision based on the destination IP address. Now, in order for, let's say, smooth routing, or for the router to make a correct action, the router must learn the direction to remote networks, or at least should know how the network or how the routers are distributed among the network. So imagine the scenario here. You have 6 routers, and you have this host number 2, and this is host number 1. And you want to send the message from host number 1 to host number 2. So this is a path here. So that's one path. Let's call it path 1. Then there is this path. So this is path number 2. You can also use this path. So that's path number 3. So there are several number of paths where the message can go to. Now, how the router pick this router or this network over this network or the opposite, that is something, it's up to the router to make the decision based on criteria or based on metrics. Could be the bandwidth of the network, or it could be the hop counts, and we're going to talk about the concept of hop in a few minutes. All right, so for the static routing, it is a program, we use program route that network administrator enters into the router. We have done that last week lab on static routing. It could be dynamic, use the route that the routing protocol adjusts automatically for topology or traffic changes. And that's the good thing about dynamic routing. The keyword here, the adjustment is automatically. Whether there is a change on the network itself or the traffic, the route will change or will be changed automatically. All right, so a quick reminder how we do static routing. The command was like this. First, we have to be at the config mode. And the command is IP route. That's the syntax. And then you put your destination network. So remember, this is a class C network, for example. So the destination network is this one that ends with 0. Subnet mask has to be there. And then you put your gateway. Gateway is like the IP address of the one in between. Yeah, the issue here, the IPs and the names of the routers. So for example, this is for Hoboken. We did not do any setup for the routers in the middle. So these commands are not going well with the figure. But if you guys remember from last week, so this is the IP address of the switch or the Ethernet switch and the router in the middle. Similar thing here for another router, it is the same syntax: IP route, destination network, subnet mask, and then the gateway. And the gateway, it is the IP address of the Ethernet in the middle router. All right, so what are the advantages of static routing? It can back up multiple interfaces networks on a router because it happens manually. The administrator can use that. And probably you can tell it's easy to configure. They're just a simple line of command. And you don't need extra resources. It's a software, just a program, a code you run. And it's kind of more secure because you are the one who decides on these, let's say, IP addresses. It's the administrator who writes these commands. Unlike dynamic routing, it's the router who will make the decision by itself. So those are all advantages, but it also comes with disadvantages. It does not happen automatically. Imagine for a large network with 100 routers, you have to do the process 100 times for a single router. So it's not kind of a practical solution. And it does not scale well in large topologies because the routing table here will look very huge. All right, so what is the need of routing protocol? That's pretty much like the example I just showed before. There are many paths where the message can travel from network A to network B. So what is the optimal route? How will the router decide to pick a certain path over the other? And in here, we're going to talk about the concept of metrics in a few minutes. But let's talk about the functions of dynamic routing. And here, the routers themselves will share information among each other. Like the routers, let's say, they will do the update on their routing tables automatically. They will share information between themselves, and the update will happen automatically whenever there is a change on the network topology. So it does not wait an action from the network administrator. Things will happen automatically here. And since it kind of monitors the network around, it determines the best path for the destination. So there you go. This is an example here where all the routers update their routing tables or their status automatically among themselves. So yeah, they pass message updates. So it doesn't have to be a message like a data message or something. It was just an update message for the routing table. Now, why is it important? What is the purpose for that? As I mentioned, updates will happen automatically. Routers between themselves will communicate. So it discovers remote networks. And the routing tables will be up to date because it happens automatically. And since the router will have a kind of general overview of their network, it can determine the best path for the destination network based on several metrics or criteria we're going to discuss later, inshallah. And that's one good thing also. Assume that let's say a path has been disconnected or broken. It will happen by itself. It will find a new best path if there's an issue with the original path. So for example, in this slide here, so assume the initial route was something like this. And there was an issue with this link. So automatically, the update will happen automatically. And there you go. And then there you go. And that's it. The message will be delivered. So that's the good thing, or that's the advantage of this way of dynamic routing. The protocols will do things automatically for you. Now, what are the components of the routing protocol? Basically, there's an algorithm. There should be some means of intelligence to the network. Algorithm, if you guys remember from the programming course, it's a set of rules that the program should obey to find a solution. And in this case, the routers will be programmed on a certain criteria on how to find the best path. So in the case of the routing protocol, algorithms are used for facilitating routing information and best path determination. And there is the routing protocol messages where the routers between themselves send update messages. So there are messages for discovering neighbors and exchange routing information. So this is like, these are the two main components for routing protocols. All right, so it's pretty much like this. Like, think about it, that this is the algorithm, this is the form of intelligence, and this one will send a message to the destination router for status update.
السلام عليكم دكتور.
Yes.
دكتور تأخرت أنا.
Okay, remind me by the end of the lecture. It's important.
Sure.
Okay. So how do we group the routing protocols? There are certain characteristics that could be grouped with. So for example, we have the routing information protocol, and that's going to be today's lab. There is the interior gateway routing protocol, and we're going to just mention it, talk about it a little bit. There is the enhanced interior gateway routing protocol. Again, we're going to talk briefly about it. The OSPF, that's going to be a topic of next week's lab. So basically, we're going to do RIP today, and next we're going to do the OSPF, the open shortest path. And there is the ISIS intermediate system. And there is the border gateway protocol. There is one important concept here, which is called autonomous system. So autonomous system is a group of routers. And basically, when we say routers, it's a group of networks. And they are under the control of a single authority. Now, we have many protocols here. How to group them? So for example, by the autonomous system connection. So for this example here, we can have interior gateway protocols and we have exterior gateway protocols. To make things simple, everything is under the interior gateway protocol except the border gateway protocol. So the interior gateway protocol, you are within the autonomous system. So imagine that like you are under the single authority, one single authority. So routing inside the autonomous system. And it is used to route within the individual networks themselves. Examples: routing information protocol, enhanced interior gateway routing protocol, open shortest path first. Now for the exterior gateway, there's only one example, the border gateway protocol. To visually illustrate this idea, this figure kind of describe it. So we have two autonomous systems. So this is autonomous system 100 and this is autonomous system 200. They're just examples, just numbers. Now, within these connections inside each autonomous system, notice we have all routing protocols here. But if you want to connect from this one here to this one here, and this one says there are two autonomous systems, we need an exterior gateway protocol or the border gateway protocol. So in the exam, you should expect a question like this. One of these protocols belongs to the exterior gateway protocol, which is the BGP, the border gateway protocol. So keep that in mind. Again, autonomous systems, like this is a group of networks or a group of routers that work under the one single authority. So for example, this is University of Dubai. That's for example here. And this is Khalifa University. Again, for example. Now, University of Dubai, they have their own networks and sub-networks and stuff. Khalifa University have the same. But if you want to do communication between these two universities, we need the BGP, the border gateway protocol. So this is for the sake of illustration and example. Okay, so that's one way of classification based on the gateway protocol and autonomous systems. Now there is another way of comparison. That belongs to the interior gateway protocol. It is the distance vector and link state routing protocols. And by the way, distance vector is an RIP protocol. RIP is an example of distance vector, and link state is OS PF. Open shortest path first. That's for the link state. So what do we mean by distance vector? Distance vector, the rows are advertised as vectors of distance and direction. That's it. So it's just a vector. The issue with that one, it doesn't give an incomplete, it doesn't give a complete view of the topology. It's just an incomplete one. In order to cover for that, there will be kind of periodic updates on the routing table, and that depends on which protocol you are dealing with. So the updates will happen periodic because it is an incomplete, it doesn't have an complete overview of the network. However, link state is the opposite. It shows complete view of the network once the topology is created. And in here, since the view is complete, there is no need for periodic updates. So keep that in mind. Distance vector, periodic updates, and incomplete view. Link state, complete view, and not periodic. So keep that in mind. So here's an example for distance vector. We have 4 routers, 1, 2, 3, 4, and there are update messages between them. This is the update message, and it's a periodic one. Now, how often the update will happen, it depends on the protocol. For example, RIP, it happens every 30 seconds. And there is another protocol, also distance vector, I think is the IGP. It happens every 90 seconds. OSPF, there is no updates there. It's a full, say, overview of the network. So yeah, these are update messages. Okay. Now this is the other one, the link state. Notice here, there is no updates, no message updates. However, within the router itself, there is a database, a link state database. All right. So that's the other way of classification based on the updates around distance vector and link state. Now there is another way of, say, when it comes to the routing updates, that's an example of distance vector. So when we're dealing with the classful routing protocols, by classful, remember the IP addresses, we made classes out of them, class A, B, C, and I think there's D and E. Now, in this case, remember these classful ones, the subnet mask for each one of them is a default. So for the first one, 255.0.0.0. While class B, the subnet mask is 255.255.0.0. Class C, we have done it also, 255.255.255.0. So since they are known, there is no need to send the subnet mask in the routing updates because it's the classful. But when we do the classless, remember when you have an IP address /23 or /25, so this is the classless one. It follows the CIDR, classless inter-domain routing information. And here, so on this one, you need to send the subnet mask. In that case, subnet mask must be shared. So this is the classful here. Like when we see 24, that's the default class C. And even like it could, you can just ignore it. But yeah, subnet mask here will not be shared. But in this one here, we have different networks. So here's /27, /30. So we have different subnet mask. In these type of networks, the subnet mask will be shared in the update messages. All right, so let's talk about metrics. So a metric is just a value, just something being predefined by the users to determine the quality of one thing or which router is better than the other. So it's a value used by the routing protocol, determined by the user to determine which router or which route is better than the other. So there is the basic metric called hops. Hops is basically the number of jumps or the number of routers that needs, well, let's say, for the message to be delivered. So for example, if I want to send a message from router 1 and I want to send the message to another computer in the same network. So in here, it's a 0 hop because I'm using only one router. There is no need for the message to travel twice. But if I want to send a message from router 1 to router 2, or basically from this network to this other network here, then I will have 1 hop. Here I will have 2 hops. So that is the thing, it's just the number of jumps. That's 1 hop, 2 hops. And that's the definition of hop. We're going to talk later in details about it, because RIP, it follows the hop count as the metric. So what are the other metrics? There are many actually. So there is the bandwidth, determines the speed of the network, the cost, and the cost will be kind of a combination of several metrics. Delay, how long for the message to be, let's say, late. Hop count, we just talked about it, load and reliability. So those are the metrics, let's say, of interest. Mainly we're going to talk about hop count and also bandwidth. So for hop count, you just count routers. But for bandwidth, it is considered, or the network speed is of importance. So for example, between router 1 and router 2, there is a speed of 56 kilobit per second. While router 1 to router 3, there is, like, say, another speed, 32 kilobit per second, for example. Then if the message, or this one, let's call it 20 kilobit per second. Now notice the aggregate speed or the overall speed is 52, which is less than 56. So probably if we are doing OSPF, which is based on bandwidth, it will take this route. But if we are doing RIP, which is the least number of hops, I will take this one. So this is RIP, and this is OSPF. So RIP chooses the shortest path based on the hop count. OSPF chooses the shortest path based on the bandwidth. All right. So yeah, these are the two main ones, and so memorize them also. A typical question as a multiple choice or a short answer, like what is the metric for RIP, what is the metric of OSPF. Some others, they have another kind of let's say metric, which could be a composite of other metrics. Okay, so where to find the metric field in the routing table? So it is used in each routing protocol. So for the RIP, we agree that is the hop count. IGRP or EIGRP, it's mainly the bandwidth by default. It could also include delay, load, reliability, but if you were asked, we're going to say just bandwidth. ISIS or OSPF, it is bandwidth. The cost, that's another metric, which is a composite of other metrics, but mainly it's bandwidth. That's the Cisco implementation part. All right, so how to see it in the routing table? So for example, we have this network, and I want to monitor the connections to R2. And let's assume we defined everything here as an RIP connection. So just show RIP count and route, sorry. R means RIP. And C means it's directly connected. So let's see how it happens. And you guys remember S stands for static. All right, so I want to check between R1 and R2, R2 and R1. So let's look at the IP addresses. So I have this one here, that's 1, 2, 3, 4. There is a 5 here. I'm looking at this one here, this value. There is 6 here, 7, and 8. So all of these IP addresses are reachable by R2. And let's see how the connections for each one of them. So let's look at the first one, the 192.168.1.0, this network. How many hops or how many routers do I need to pass to reach there? So that's 1, and there you go. The switch doesn't count. So in here, this is the value here. This is the hop count. So how to see the hop count? First of all, make sure it's R, that is an RIP protocol, that's 1. Then the value of the hop count will be at the second value between the square brackets. This value, we're going to talk about it later, that's the administrative distance. All right, so this is an RIP, there is administrative distance, and there is the hop count. Now, what about 192.168.2.0? Now, 2.0 is this one, so it reaches this router, and this is directly connected. So there is no need for a routing protocol here. It's directly connected. So there is no information about hop count or administrative distance. In fact, directly connected, it has an administrative distance by, if I recall well, 0. For the other network, 3, again, directly connected. 4, this is 4 for this router, directly connected. Oops. Now let's see with 5. I have this one, 5 here. And let's see how much routers are needed to reach that destination. That is 1. And there you go. Should be 2, but for some reason it's showing that here the distance is 1. But we'll take it as 2. For me, I will take it as 2 because there are 2 routers were involved. And the administrative distance is 120. So this is also an RIP connection. Now, what about 6? Now, for 6, there are 2 ways to reach it. Whether it was by reaching R1, then to go to this network, or R3 by this network. And let's see how it happens. So you can have via 192.168.2.1, so by following this IP address, so this router, or via 192.168.4.1. So I have 2 paths, and that's the good thing about it. So this means that it shows an idea about what are other alternative routes. So if this one is broken, this one is already there. If this one broken, this one is already there. And again, for each one of them, it shows the administrative distance and the hop count. And since it's only one router, the hop count is 1. Now 7, similarly, it is only 1 RIP. Now what about 8? So 8, it will take it this like this. That is 1, and that is 2, and there you go, that is 8. So in this case, the hop count is 2, administrative distance is the same. It's going to stay always 120 for RIP protocols. So yeah, this is how it finds the connection or routing table. So this is kind of a routing table for R2. This is how it monitors all other routers. All right. There's something called load balancing. Basically, load balancer, sometimes when you are dealing with networks, when you have too many connections, you don't want to overwhelm a router or a device with many messages. So the job of the load balancer is to make sure that the routing is fair and is distributed, and packets are distributed evenly among multiple same cost paths. So pretty much like this. These 2 routers have the same cost, so the message could be delivered in both cases, and that's what the load balancer does. So what will happen, even if this one is broken, this one will be delivered. So when you have 2 equal cost paths, the message will be sent twice. You always prefer the lowest cost, but when you have two connections with the same cost, you send over the two connections. All right, administrative distance, why it's needed, it's calculated value used to determine the best path to a destination. So it is a calculated value. We will not go into the math behind it. We'll just take the value because packet tracer or the default for so many routing protocols, the default is there. So what is the purpose? It's a numeric value that specifies the preference of a particular route. So here is an example. Here we have two networks, RIP and EIGRP. For the RIP, the administrative distance is 120. And for the EIGRP, the Enhanced Interior Gateway Routing Protocol is 90. Keep in mind that R1 and R3, showing here, that they are not on the same routing protocol, so they cannot communicate between themselves. All right. So how to define the administrative distance for multiple routes? This table here, I think, is in the next slide, actually. How to find it? It is the first number here. So in this one here, it is D, that is like stands for the EIGRP. For example, it is 90 for this router. And the others, if it's R, that is 120. And notice one thing here. If it's an RIP, there will be administrative distance and hop count. But if it's a different protocol, it will show the administrative distance along with another value. This could be the cost. This could be another metric. It doesn't have to be a hop count. But always the first value will be the administrative distance. The second value will be the metric that is based on. All right. So this table here, yeah, when you have direct connection, administrative distance is 0. EIGRP, there is a summary count version, that is 5. EIGRP, the internal one, 90. The external one, 170. RIP, 120. OSPF is 110. IGRP is 100. And by the way, I'm expecting at least you memorize connected, EIGRP, OSPF, and RIP to memorize. All right. So that's a typical question I will ask in the exam. What is the administrative distance of a certain protocol? All right, now we're going to put a little bit of focus on the RIP itself. The key characteristics are as follows. So it is a distance vector, so updates will happen periodically. And in here, the period is over 30 seconds. The hop count here is the metric that we monitor. And there is one thing, actually, there is a maximum count for the hop counts. If it exceeds 15, it will drop the message. And we'll see why this feature is there, or this characteristic is there for the RIP protocol. The configuration, we're going to do it in the lab today, but it is extremely simple. So you are at the router, just put router RIP and put the network and your network, the router network. Now we are not looking at the destination network, because in this one it shows the router network, and this is the message, the update message that will be sent to all other routers. That's as simple as it goes. So for each router, based on how many networks are connected to that router, you put this command. Okay, so in here you don't worry about any subnet addresses or individual host addresses. Okay, so here's a configuration example. So assume that we are router BHM. Router BHM is connected to 10.0.0 and 192.168.13 and 0. I'm looking at the network address. So first, you are in the config of BHM, just say router RIP, then just put the network address for this IP and the network address for this IP. So this is the class A, So the network address will be 10.0.0.0. That's a class A, number 10. This is the class C. The network address is 192.168.13.0. So that's it. That's for router BHM. Now router GAD. GAD is connected to two networks. 192.168.13.0. It's class C. Similar thing here. 192.168.14.0. Similar command. Router RIP. Just here. Network 192.168.14.0 and 13. Similarly for BOAZ, we have network 14, and this is the class B network, 172. There's going to be 00 for the network address. And there you go, 192.168.14.0, 172.31.00. This is what we're going to do in today's lab, and the architecture actually, or the network, is similar to this one. I will have 3 routers, exactly like last week, and I'm going to just put the commands. And we'll see how easy the lab is. How to verify the RIP configuration, just type the command show IP protocols for that particular router. So in this case, that's the GAD router, which is the one in the middle. Show the RIP protocols, then it will say that is, oops. Okay, something is wrong. All right. So RIP updates happen every 30 seconds. And the next one will be due in 5 seconds. It shows when the next update will happen. So after 180 seconds, the message will be considered as invalid because of the delay. It will hold down for another 180 seconds. And
مرحبا دكتور.
Yes.
How are you?
Alhamdulillah. Did you just log in?
دكتور متى attendance؟
I took the attendance already. So make sure you remind me at the end of the lecture.
دكتور I was in bathroom.
That's no problem. Just remind me at the end of the lecture.
Okay, doctor. Thank you.
Right.
You are the best.
Okay, so outgoing updates, filter lists. Let's not worry about those. We'll go to this one. So routing for networks. So this is the previous one here. So it routes to these two networks. I think that's a different example. Now it's a different setup here. But it just says that verify the RIP interface. That's the gateway. But this is the information that we're going to monitor in today's lab. Okay, now what is the issue with the routing loops or for RIP? We are counting hops. But what if the connection is closed? Let's say at my destination, the connection is like there's a problem. The connection is broken. So the message will keep traveling over the network until infinity. So network 1 here is unreachable. And I want my destination to reach network 1. So it sends to this message. There's no connection here. It will go back, send to this one. No connection, and so on. It will keep doing that infinitely, and that's what we go into something called infinite or counting to infinity. The message will keep hopping over the network, wasting time, taking bandwidth, and the distance vector will be incremented. So the solution for this one is to put a limit or a maximum. And that's why in RIP by default, the hop count is 15. If you exceed 15, the message will automatically be sent to the recycle bin or will be flushed or trashed. So the maximum metric here is 16. So the 15 will be count. So if I ask you, what is the issue with RIP and how to solve it? The issue with RIP, when you have counting to infinity, it will keep, the message will keep jumping until it reaches the destination. And if the destination has an issue, the message will be there and the network doing nothing. So the solution, define a maximum. Please mute yourself. Everybody, please put yourself on mute. All right, so let me share my screen again. All right, so we were at this point, define the maximum. Okay, so define a maximum is the solution for counting to infinity loops. IGRP, that's another kind of protocol. It's the interior gateway routing protocol. It is also a distance vector. In here, the periodic update happens every 90 seconds, unlike RIP. RIP happens every 30 seconds. The main metric here is the bandwidth, but they all create a composite metric: bandwidth, load, delay, and reliability. Similar setup, you just say router IGRP 101. And we'll talk about these details of 101 later in the lab, inshallah. And this is the same syntax. So you just need to identify the protocol here. Similar thing here, network. Yeah, these packet tracer commands, I will leave them to the lab for the details. So here's a quick comparison between RIP and IGRP. The metric is hop count, and maximum count is 15 routers or 15 hops. It was originated by Xerox company. IGRP, it is a composite metric of all those. And this one has no limit technically, but it is limited to 255, because here it's not about the hop count, or it's not about the jumps of the message. And it was developed by Cisco. So by now, I think we all agree that the routing metric is used to determine the best path for the next hop. All right, the last protocol we're going to talk about is OSPF, open shortest path first. So there is the concept of area, and that is something for the network administrator to use. So we have two areas in this one. So a collection of networks and routers that has the same area identification. And by the way, area here is a logical area, it's not physical area. And is set up by the user. He's the one who decides which area is area 1 and which area is area 2. So each router within an area has the same link state. So there you go. This is a link state routing protocol. It's not distance vector routing protocol. There's no routing updates that happens here. So a router within an area is called an internal router. That's a definition. So the link cost here will be based on many factors, but one of them could be the bandwidth. So the value assigned to a link, rather than hops, link state protocols assign a cost to a link. So here the cost will be based on the bandwidth of the link, the transmission speed. So the faster, probably the lower cost. So yeah, there you go here. The cost here, it is based on the bandwidth. That's for OSPF. How to do that? Router OSPF, and there is a process ID, and then you define the areas later. And there is a concept here of inverse mask. I will not bother talking about it right now. It's going to be the topic for next week. We're going to talk in details about what this is, inverse mask, which is basically the inverse of the subnet mask. So if the subnet mask is 255, 255, 255, 0, then the inverse mask will be 0, 0, 0, 255. This is what we mean by inverse mask. Now the area ID, it's up to the user. In fact, I think this should be one line. So discard. All right, yeah, something like this. So let me make the text a little bit. Yeah, there you go, way better. Okay. So the router OSPF subordinate command that defines the interface by network number that is OSPF will run on. Each network number must be defined to a specific area. So again, the syntax for the OSPF will be the topic for next week. Here is the setup. So you put the identifier number you want. It's up to you. And the same thing here, OSPF 250, like 50, they have nothing to do with each other. And you identify that's area 0, and then that's area 0, area 0. All right. So similarly, show IP protocol, show IP route OSPF, show IP interface. That's going to be again the topic for next week. Remember, S is for static, R for RIP, O is going to be for OSPF. I think we have seen D. C is connected, like I said, directly connection. I think we have seen D a couple of times ago. There you go. It is EIGRP. That is D. All right. So that's it for the lecture.